Okay, good afternoon, dear students. In last class, we discussed about the difference between electrolytic and metallic conductor. In today's class, I am going to discuss about the specific conductance, the definition of specific conductance and unit of specific conductance and equivalent conductance and molar conductance and effect of dilution on conductance. Unit is conductance. In this first one, specific conductance. Specific conductance. Here, this specific conductance is directly proportional to the length and inversely proportional to the area of cross section. The specific conductance is defined as the specific conductance is the directly proportional to the length and inversely proportional to the cross section of the cross section area of cross section. Here, this is a directly proportional to the length, that is L, and inversely proportional to the area of cross section. And this is inversely proportional to the area of cross section. Area of cross section. Area of cross section. Area of cross section is denoted as this is area of cross section and L is a length here. You know here the specific conductance is denoted as the symbol is lambda. This is a capital lambda, or you can write you can denote this small lambda. Here denoted as lambda. So here, or it is the name is K, that is kappa. Constant for K here. This is denoted as, this name is, okay. Can write 1 cube here, the length and area of cross section, and here 1 centimeter length. This is a cube, and here this is a positive, and here this is a negative. This is positive end and this is a negative end. And this is conductance of the cube. This one is conductance of the cube. This is the conductance of the tube. And here this is a 1 centimeter and this is also 1 centimeter. That is a specific conductance. This is 1 centimeter and this is 1 centimeter. This is a specific conductance. In this is a tube, and here this tube is consist of the conductance of the tube, and here this difference is distance is 1 centimeter, and here this is also 1 centimeter distance. This is known as the specific conductance. Here this any of the here the substance which offers very little resistance to the flow of current. Here the substance and it which offers the current, that it offers the any of the little resistance to the flow. Here this is the substance, it is offered to the resistance, that is a little resistance to flow of the current, which is in turn allows the more current to pass through it. Here more current to pass through it, the power of a substances to conductance. Here substances which have little resistance, and here is a flow of current. Flow of current which is in turn allows the current to the pass through it. Power of the substances to conduct electricity. Here the power of the substances. Here the power of substances is to conduct the electricity will be the reverse of the its resistance. Here this is the it conducts electricity, and here the reverse of the resistance. Here the reverse of the resistance. Reverse of the resistance, and therefore the reciprocal of the specific conductance is known as here the reciprocal of the specific conductance, that is specific resistance. Reciprocal of specific resistance. Reciprocal of specific resistance. Here the substance is offered little resistance, and here it conducts the flow of current to conduct the power of the conductive electricity conducts this substance. Here that is a reciprocal of the specific resistance, and this term is known as a specific conductance. This term is known as this specific conductance. Here the specific conductance can be defined as the definition for specific conductance in your examination arises question, define specific conductance, or what are specific conductance. Here the specific conductance is defined as the conduction or the conductance of 1 cubic meter. This is a conductance of 1 cubic meter cube of a solution. Here 1 cubic meter cube of a solution of an electrolyte. You take an electrolyte, that is any of the electrolyte, that is strong electrolyte and weak electrolytes. Here the conductance of 1 cubic meter cube of a solution of an electrolyte. This is known as a specific conductance, or it also, in other words, to define or this specific conductance, the conductivity offered by the solution. In our solution, the conductivity is offered by a solution of the length, that is 1 centimeter. Length is 1 centimeter and having the unit area of cross section. This is called as a specific conductance. Here the specific conductance is denoted by this one. The specific conductance is denoted by kappa, that is K. K means this is it is known as kappa. The specific conductance is denoted by kappa K. That is, this is a symbol, kappa symbol here. And the unit of this specific conductance is per ohm per centimeter. Unit of this specific conductance is per ohm per centimeter. Per ohm per centimeter. You can write another symbol, Simon per centimeter. Simon per centimeter. I write another symbol, Simon per meter. Simon per meter. Here the per ohm, that is 1 per ohm is equal to Simons. Per ohm is equal to Simons. This is equivalent to this one. The unit of specific conductance is per ohm per centimeter or per Simon per centimeter or Simon per meter. This is Simon. S means Simon, and here per ohm is equal to Simon. That is Simon means S. This is S. This is very important for 1 marks question. I write here the definition of specific conductance. Definition. Conductance of 1 cubic meter or 1 cubic meter. Conductance of 1 cubic meter. Conductance of 1 cubic meter of 1 cubic meter of or 1 cube meter. Cubic meter, cube of a solution of an electrolyte. Cube of a solution of an electrolyte. Solution of electrolyte. The solution of electrolyte means here 1. Here the conductance of 1 cubic meter cube of a solution, and cubic meter cube of a solution of a electrolyte. This is a definition of specific conductance. Specific conductance. And another definition or another definition, the conductivity offered by the solution of the conductivity offered by the solution of 1 centimeter length. Solution of 1 centimeter length. Here we having a unit of area of cross section. Having unit of area of cross section. Area of cross section. These are the definition for specific conductance. Here the definition of specific conductance. Conductance of 1 cubic meter of cube of a solution of electrolyte. The cube of a solution of electrolyte, take any of the example HCl or another NaCl, any of the, you take any of the electrolyte here. The conductance of 1 cubic meter cube of a solution of electrolyte. This is known as the specific conductance. Or another definition, you write in your examination this definition: the conductivity offered by the solution of 1 centimeter length having the unit of area of cross section is called as a specific conductance, and this is denoted as the symbol is K. That is, this is known as a kappa. And here the unit is, you know already, the unit of specific conductance is, that is a per ohm per centimeter, or Simon per centimeter, or Simon per meter. Here I will write the unit of specific conductance. The specific conductance here unit, the specific resistance, the specific resistance or resistivity, or it is also known as the resistivity. You write this here. Or this resistivity or specific resistance. The specific resistance is the rho is equals to, here rho is equals to R into A by here. R into A by here. Here the specific resistance is direct. This is a R, and here this is a A by L. A means the area of cross section, L means length here. And you take the R is resistance. The resistance, you know, ohm. Here A means area. Area is centimeter per centimeter square divided by length means in centimeter. You take in centimeter here. Ohms, centimeter square, centimeter here. This square, centimeter square, and this centimeter, it comes ohms, centimeter. Ohms centimeter, and the specific conductivity or specific conductance. This is a specific resistance symbol. This specific resistance unit, and the specific conductivity. Specific conductivity or conductance unit. Here this is written as, that is kappa, that is K here. Therefore is equals to, it is inversely, that is a reciprocal of this specific resistance. This reciprocal of specific resistance 1 by 1 divided by here. Therefore this is equals to 1 divided by this rho means here O per centimeter. Ohm, so O centimeter. You write, you take denominator goes to numerator, it is a per ohm per centimeter. Here this is equals to per ohm per centimeter. This is a unit of specific conductance. This is unit of specific conductance. In SI system means that is a Simon per centimeter. Simon or Simon per meter. This is a SI unit. Simon per unit per meter or Simon per centimeter. These are the SI units. Are you right? Per ohm, this is a symbol. This per ohm, therefore is equals to this per ohm per centimeter. Right? This type of. Okay, this is a specific conductance. Next, the equivalent conductance. Next, equivalent conductance. Equivalent conductance. Here, the equivalent conductance, this is denoted as lambda. That is capital lambda. Or you take or this lambda. Okay, here the equivalent conductance is what is meant by equivalent conductance or definition of equivalent conductance. Here, the equivalent conductance is defined as the conductance of an electrolyte obtained by dissolving 1 gram of equivalent of an electrolyte. Here, the equivalent conductance is defined as the conductance of an electrolyte obtained by here the conductance of an electrolyte. Here the conductance and this is a equivalent. The conductance of an electrolyte is obtained by dissolving 1 gram of equivalent of an electrolyte. Dissolving 1 gram of equivalent of an electrolytic solution. That is like 1 gram of equivalent of an electrolyte in water or electrolyte 1 gram of equivalent of an electrolyte in water. It dissolved in water. This is known as the equivalent conductance. You have some volume here. You taken some volume of water. This is water and dissolved 1 gram of equivalent of an electrolyte in water is called as the equivalent of a conductance. And this is denoted by this lambda or this lambda. This is capital lambda and this is a small lambda. And this equivalent conductance will be equals to the product of the specific conductance. This equivalent conductance is the product of the specific conductance and the volume containing 1 gram of the equivalent of the electrolyte, and it is represented, the equivalent conductance is represented, that is lambda is equals to here, this is the equivalent conductance is equals to the product of the specific conductance. Here the specific conductance is K, that is kappa. Here this is K, kappa, that is lambda is equals to, lambda means equivalent conductance. Equivalent conductance is the equal to the product of this specific conductance and volume of the electrolyte solution. The volume of electrolyte, this is volume is written as into P. This is a equivalent conductance. And here the V is the electrolytic solution containing 1 gram of equivalent of the electrolyte. Here, this is a equivalent conductor where V means it is volume. The volume of the electrolytic solution. V is the volume of the electrolytic solution. Volume of the electrolytic solution containing 1 gram of equivalent of containing 1 gram of equivalent of 1 gram of equivalent of the electrolyte. Equivalent of the electrolyte. This is a, and here in one way the volume of the electrolytic solution containing, you have solution is contained 1 gram of equivalent of the electrolyte. This is the definition of equivalent conductance. Here in general, if an electrolyte solution contains n gram of equivalent. For example, in general, here you know already it containing 1 gram of equivalent of the electrolyte. For in general, in equivalent conductance, here 1 gram is it contains n gram of equivalence in 1000 cc. For example, n gram of equivalent of the electrolyte contains 1000 cc or 1000 ml. The 1000 cc of the solution, the volume of the solution containing 1 gram equivalent. Here, the volume of the solution containing 1 gram of equivalent will be written as 1000. Here 1000 divided by this. Here taken n is a in general, that is a normality. Here this is a 1000 cc divided by n. Here the above equation volume is get. Here this is the volume is taken lambda is equals to k into volume is 1000 cc divided by n. Here you get this is equals to lambda is equals to kappa multiplied by this one 1000 divided by capital N. Okay, here this is a equation for in general taken as n is n gram of electrolyte. The n gram of electrolyte n gram of equivalence, it contains n gram. Any of the substance you or electrolyte or solute here. General, the electrolyte solution contains n gram here. In n gram of the equivalent in 1000 cc. In 1000 cc of the solution, the volume of the solution containing 1 gram. The volume of the solution containing 1 gram equivalent will be obtained, that is 1000 divided by n, and here this is equals to V. Volume, you know, volume is contained 1 gram. Equivalent here you write this 1000 cc divided by n is replace here the V value 1000 divided by n. This is a formula for equivalent conductance, that is lambda is equals to k into 1000 divided by n. Here the unit of equivalent conductance unit is Simon square per equivalent. Unit Simon per equivalent. Simon per equivalent, or in assignment Simon square per equivalent. So here the Simon square I will write as E. Simon square per equivalent. Here this is a in SI unit. Here SI unit is a Simon square, or you write SM. And this equivalent conductance I will write, you write here m square. Here Simon, this is a Simon meter square per equivalent. You write per centimeter, or sorry, meter or centimeter. Simon centimeter per equivalent, or Simon meter square per equivalent. This is a unit. And right here unit of this equivalent conductance, that is unit of equivalent conductance. Equivalent conductivity. Here the formula, you know the formula is here. Therefore lambda is equals to k kappa multiplied by 1000 divided by m. Okay, here k into 1000 divided by n, and n is here the normality. Normality, right? The n is a normality. Therefore, this lambda is k into 1. Okay, k into 1. Here, you know, this is a specific conductance. The specific conductance, that is lambda is equals to, specific conductance means per ohm per centimeter. Per ohm and per centimeter, and the volume is cm cube divided by gram per equivalent. And here ohm, this unit per ohms per centimeter multiplied by cm cube divided by gram equivalent. Gram equivalent. Here this is the unit of the specific conductance. Here lambda is equals to kappa into volume, and here the lambda is equals to kappa means the product. Here the equivalent conductance is the product of the specific conductance and volume of the electrolyte. Here for specific conductance is the per ohm per centimeter, and volume unit is the cm centimeter cubic centimeter divided by gram per equivalent. That is the normality is a gram per equivalent. And here therefore is equals to the equivalent conductance unit is per ohm per centimeter, and here per ohm per centimeter means here this 3 minus 1 here 2, and this here per ohm per centimeter. Therefore is equals to per ohm, and here centimeter square remaining centimeter square, and gram equivalent per gram equivalent or per equivalent. And here gram per equivalent. Gram per here gram per equivalent per here. This is a unit of equivalent conductance. Or you can write therefore this is in SI unit here Simon centimeter square, Simon centimeter square, and here per equivalent. Gram per gram per gram per equivalent are this is. Here this is a equivalent conductance unit. Simon centimeter square per equivalent. In SI unit, in another form here, in SI unit, you can write this lambda here. This is a lambda. Therefore, this is equals to the Simon. This one Simon centimeter square and per equivalent. This 1 Simon centimeter square per equivalent. Therefore, this is equals to 10 to the power of 4. 10 to the power of 4 Simon centimeter square per equivalent. Here, according to SI unit, here 1 Simon centimeter square per equivalent. Therefore, this is equals to 10 to the power of 4. 10 to the power of 4 multiplied by Simon centimeter square per equivalent. This is a SI unit. And right here, finally the definition of this equivalent conductance. Very important. One is the definition of equivalent conductance, definition of specific conductance, and unit of equivalent conductance and unit of specific conductance, definition of molar conductance and unit of molar conductance. This is also 1 marks question, and unit also 1 marks question, definition also 1 marks question. Here, equivalent conductance definition. The conductance of an electrolyte, is obtained by dissolving 1 gram equivalent electrolyte obtained by dissolving 1 gram equivalent of 1 gram equivalent of 1 gram equivalent of an electrolyte. 1 gram equivalent of an electrolyte. 1 gram equivalent of an electrolyte in water. So this is definition for the equivalent conductance. Here, the conductance of an electrolyte is obtained by dissolving 1 gram of an electrolyte in water. This is you write in your examination definition for equivalent conductance. This is the important question. 1 mark question is added in your examination. Okay, next, the molar conductance. You write the symbol is lambda base 1 on mu. The symbol for molar conductance. molar conductance. Here molar conductance, and here the molar conductance is defined for very important question. This is a 1 mark question. Molar conductance, specific conductance, equivalent conductance. Here the molar conductance, it is defined as the conductance of the solution obtained by dissolving 1 mole of the electrolyte in water. Here the conductance of the solution obtained by dissolving 1 mole. See here the difference in equivalent and molar. Molar conductance and equivalent conductance. In equivalent conductance, 1 gram of equivalent. 1 gram of equivalent. And here 1 mole. In molar conductance, that is a 1 mole of the electrolyte. 1 mole of electrolyte. Here 1 gram of equivalent of equivalent of an electrolyte. Here 1 mole of an electrolyte. Only this difference for equivalent conductance and molar conductance. Here the molar conductance is obtained by dissolving 1 mole of an electrolyte in water is called as a molar conductance. And in other words, it can be defined as the conductance in another definition for this molar conductance, and the conductance due to all the ions produced from 1 mole of the electrolyte. All ions here, all the ions are produced from 1 mole of electrolyte here. The ions are present here, the 1 mole of electrolyte at a given concentration. And this, it is the molar conductance is denoted by the unit is Simon centimeter square per mole. Here Simon centimeter square per mole. Here you taken mole means per mole, and here you taken equivalent means per equivalent. Only this difference per equivalent per mole. Here same Simon centimeter square per mole. Okay, I am right here the definition of molar conductance. The conductance of the solution. Conductance, this is a definition. Conductance of the solution obtained by dissolving obtained by dissolving 1 mole of an electrolyte in water. 1 mole of an electrolyte in water. This is the first definition, 1 mole of an electrolyte. In other words, here it is also defined as for another definition for molar conductance. Here the conductance due to all the ions. Conductance due to all the ions produced. All the ions produced from 1 mole of the produced from 1 mole of the electrolyte. Here the presence of 1 mole of the electrolyte, 1 mole of the electrolyte at a given concentration. At a given concentration. You write this definition also. And here this is denoted as m micro mu or m. Or you can write this lambda m. Okay, the symbol for this molar conductance mu or m or lambda base m. These are the definition. Conductance of the solution obtained by dissolving 1 mole of electrolyte in water, or conductance due to all the ions produced from the electrolyte. Here produced from the 1 mole of the electrolyte at a given concentration. And these are the definition for molar conductance. Here the molar conductance, unit of molar conductance, unit of molar conductance or conductivity. Molar conductance, unit of molar conductance is, that is, you know already, lambda m is equals to kappa multiplied by, okay, multiplied by V, you taken here the concentration. In that equivalent conductance, you take a normality. In molar conductance, you take molarity. Therefore, this is K kappa into 1000 divided by 1000 divided, sorry, here you take the equivalent conductance is N. N means normality. Here you take 1000. C means, that is molarity. Therefore, is equals to kappa K multiplied by 1000 divided by molarity. Divided by molarity. Right? This symbol, you know this. For this one, molarity, and here 1000 divided by molarity, and the unit is obtained here per mole, per centimeter square, and per mole. Here K is the specific conductivity and C is the, or it is K is the specific conductivity, V is the volume of the solution containing 1 mole of electrolyte, and C is the molar concentration. Here where C is the molar concentration. Molar concentration. Finally, you get this unit of this molar conductance, that is per mole centimeter square, per centimeter square per mole, per mole. So this is the unit of molar conductance. Okay, I will stop here in class and continue in next class.